Stokes theorem is another one of our theorems we cover in multivariable calculus. In this theorem, we are seeing the equivalency between surface area. So pretend you got a surface, and we want to integrate not F, not a vector field F, but a different vector field, the curl of F, which gives us the flux of the curl of F. And that is equal, identically equal, to the line integral over the boundary of the surface. So instead of integrating through the surface, which could be quite complicated, it may be easier to integrate doing a line integral over the boundary. Now, in this case, for instance, this boundary would have to be broken up into 4 boundaries. I doubt we could do this with one parametric equation for the curve. So perhaps the curve, the line integral rather, would be more difficult than doing that. It really depends on the surface and on the boundary of the surface. So this boundary is complicated, for instance. Perhaps, again, it may be easier to do this through the curl. There are instances where the boundary of the surface is simple. For instance, circles are reasonably simple. So if you have a circle as the boundary, but then the surface we are integrating over, so this is the surface, is very irregular and it would be very difficult. But pretend the bottom is a circle. This kind of reminds me of a chef's hat. So yeah, this is all one surface. As you can tell, figuring out the surface integral, which would be the flux with this vector field, which is the curl of another vector field, F, that would be way difficult, in my opinion. It would be way easier to just take this guy and go around and do the line integral around the boundary. But in this case, and we don't know, we really have to do this in a one-to-one case and see which one is easier. Oftentimes it is a good idea to do both ways so that we can practice how to handle Stokes theorem. Yeah, in this case, perhaps finding the boundary will be more difficult, but sometimes the boundary makes things actually easier. You know, even if we have 4 or 5 sides or more sides to a boundary, perhaps that is simpler. We're going to do a couple of examples, at least one example, to see how this works. So here's our first example. It may be the only example, and we will just add more comments to this example. Pretend you have a surface. So remember, we are talking about a surface. One surface that is made up by this. So the surface has only 2 faces to it. We can divide it rather in 2 faces. So we got the top, and we got around this, but we don't have the bottom. So with or without bottom lid. So no lid in the bottom. It's you can actually go through. Yeah. So if we wanted to do that, well, I haven't finished this. I have to tell you what we plan to do. We want to find the double integral over this surface. So the whole thing, we're going to label it as S. Perhaps we can label the top as S1 and the side as S2. There is no bottom. of the vector 0, 0, 2 with respect to the surface. So pretend we wanted to do that. As long as we have piecewise continuity, we are good. We don't have to have, as in those cases, a nice smooth continuity all over. If the surface is piecewise continuous, we are okay. So here we have to bend, quite a bit of an angle to get to this, from this surface to this surface, but it's still a piecewise continuous surface. So we're okay. For the formal statement of Stokes, this is informal because I'm only showing you the equation that goes with Stokes theorem, but you should really read the book, whichever book you're using for multivariable calculus, because they will have a formal statement of the theorem with all the premises and hypotheses and so forth, conditions for which the theorem will work. Generally speaking, if things are nice enough, things will work. Okay, so it turns out, so again, if we wanted to do this, we can find the double integral over S1 over S2, assuming that the top is labeled S1 and the side is S2, and that's it because there's no bottom. And then we will have to do this with the two surfaces and figure out the answer. Or if we apply Stokes theorem, then we can do this integral instead as a line integral of a, oh, now we would have to have this as the curl of something else. It turns out that this vector field 0, 0, 2 could come from many different vector fields, but it turns out that the curl of negative y comma x comma 0 is equal to, well, we can kind of try to do it. Remember, the curl is the cross product of the gradient and the vector field itself. So if we use the gradient, we would have, remember, the gradient would be the derivative with respect to x, derivative with respect to y, derivative with respect to z, crossed with this as an operator. So we would have 0, 0, because that would be the derivative of x with respect to z, which would be 0. And then if we go this way, we have 0, because there's a 0. Derivative of 0 is 0 regardless of the variable we integrate with respect to. And then the derivative of negative y with respect to z would be 0. And finally, we would end up derivative of x with x, that's 1. And then derivative of y with respect, derivative of this y with respect to y, that would be 1. And then work out the negatives, because there's a negative here, but there's a negative from the cross product coming up. So we end up with 1. So indeed, the curl of this vector field is 0, 0, 2. So according to Stokes theorem, this is the same thing as negative y comma x comma 0 dr, where r would be this path, just this circle. Oh, I did not tell you what this is. In fact, on purpose, I'm not going to tell you the top. All I'm going to tell you is that this is the unit circle. So that is the unit circle. All right. So let's write some equations for the unit circle. R of t could be, as we know quite well, cosine of t, sine t, and 0. And then what do we have to do in this case to find the line integral? I think that's, oh, we have to find dr, which would be, dr would be derivative of cosine, which is negative sine t, derivative of sine, which is cosine t, and derivative of 0, of course, is 0 dt. We gotta find the differential. So, and by the way, t goes from 0 to 2 pi because we are integrating over the entire circle. So this is the same as 0 to pi, negative y. Now mind, this is x, this is y, and that is z. So negative y would mean negative sine of x, rather sine of t. Negative sine t. X is cosine of t as the second component. And then 0. And we're going to multiply with a dot product with dr. dr is negative sine cosine 0. That's a coincidence. We have exactly the same thing. Well, sort of a coincidence. And then let's put the dt at the end. So this is one line that I have broken because I don't want to get into the next column. So let's put the columns here, I suppose. There we go. So the dot product, of course, is going to be negative sine. Well, sine and sine, that's going to give us sine squared. The negatives simplify. So we have sine squared t. You guys know where this is going, cosine squared of t. And then plus 0 squared, just for the record, even though we shouldn't put it there, but still. So that's going to be 1. We're integrating 1 from 0 to 2 pi, and of course the answer is 2 pi. So notice we obtained the actual surface area, the surface integral rather, over this compound surface. It's a surface made up by this lid on top and then the side, without actually figuring out the surface area directly. The reason is because we have Stokes theorem and because we have a vector field for which the curl is the given problem. One of the complications with Stokes theorem is that if you're finding the flux, this is the flux of this vector field over this surface. If you want to find the flux, you would have to find and using Stokes theorem, if they don't give you the vector field whose curl is the one here, then you might have to find that out, and that's not easy. It's kind of like finding the antiderivative. We would have to find the anti-curl, in this case, to make Stokes theorem work. So it took me a little while, but not too long to figure out the curl for this vector field. So again, I didn't tell you this. Let's do this problem again without Stokes theorem and see what the answer should be. So example 1 again, without, I should use a capital letter, so Stokes theorem. Yeah. All right. So now I have to be more precise. I have to tell you the equations of the, well, in particular, the equation of this guy, which is going to be z equals 2 plus y. So it's a plane, on three-dimensional plane. I think we've seen this before. And then this would be the unit circle on the xy plane. So the plane goes, this is the x-axis, the y-axis, and then the z-axis would go up. And let's label this as S1 and the side as S2. And okay, so if we want to find the double integral over S1 of 0, 0, 2 with respect to the surface, we have to parameterize that surface itself. So the way we can parameterize S1, let's see, we're going to use R of UV, and boy, I think it will be easier if we use x and y, if we use a parametric, rather a trivial parametrization. So put x where x goes, put y where y goes, and then z, well, z is equal to 2 plus y, 2 plus y. There we go. Yeah, so if we want to do this directly, if we want to do the surface integral, remember how we do that. We have to, once we have the parameterization, we have to come up with a parameterization. That's job number one. Job number two, we got to do some computations. Our r sub x, in this case, would be 1, 0, 0. R sub y would be, let's see, 0, 1, 1, 0, 1, 1. And then we do the cross product, and that's going to give us 0, and then negative 1, yep, and then 1. So this double integral will be equal to the double integral of 002 dotted with O negative 1, 1, O negative 1, 1, with respect to the area over D, and D would be the circle down here on the floor. Okay, so technically speaking, we would have to go, say, from negative 1 to 1, from negative square root of 1 minus x squared, and to the positive 1 plus x, 1 minus x squared. Yeah, you know, this is still the unit circle. But let's simplify our work. Well, this dot product is going to give us 2. So we can factor out the 2 and we just end up with 1. And remember, finding the double integral with respect to the area of a region is the same thing as the area of the region. So, and this is the unit circle. We know the area is pi. And so when we factor out the 2, we're just going to end up with pi for the double integral times the 2 that we factor out. So the answer would be 2 pi, which makes sense because there is a vector field going up. So how much is going through this membrane, the area of the membrane, times the magnitude of this vector, which is 2. This is a pretty straightforward kind of problem. All right, now that's S1. That is S1, the double integral over S1. I think I'm going to need another piece of paper. Let me do that here. 2, 3. I'm putting pages on my sheets. So now let's do the same thing over S2. All right, so we need to parameterize this guy. I'm going to parameterize it here. So we're going to use R of U V. All right, so first we want to go around, and that can be created by using cosine U, sine U, and then we're just going to use V for the height. U goes from 0 to 2 pi, and that causes us to have to go around this circle on the bottom, the unit circle, and V is the Z component. Now the Z component can go up to this line or this plane. This plane is y plus 2. So V can go from 0 from the bottom up to this plane, which would be y. Remember, this is x, this is y, and this is z. So y plus 2 would be 2 plus sine of u. All right, so that is the parameterization of this surface, S2, not the top, not the bottom, nothing, just the side. And then, let's see. We still need to do r sub x because we're doing the surface integral, not r sub x, rather r sub u, because now the variables are u and v. Whoops. And that would be negative sine u, cosine u. Derivative of v with respect to u will be 0. R sub v, well, that would be 0, 0, because there's no v's. And 1. R sub u crossed r sub v. Okay, so that is cosine of u. Yep. And then, negative. Oh, but there is another negative. So there is actually just sine of u and then 0. Okay, so the double integral over S2 of 0, 0, 2 with respect to the surface is the double integral of 0, 0, 2 dotted with cosine of u, sine u, 0, and I don't have enough space to put the differential. We have to put it there. Well, v is limited, so dv should be first and then du. V goes from 0 to 2 plus sine of u, and then u is going from 0 to 2 pi. So that will do it. Okay, but notice that 0, 0, 2 dotted with cosine, sine, and 0 is going to give us 0, because 0 times that is 0, 0 times that is 0, 2 times 0 is 0, and we add those three products together. So we end up with 0 plus 0 plus 0, which of course is 0. So we're going to end up integrating from 0 to 2 pi, from 0 to 2 plus sine of u, 0 with respect to u, rather with respect to v. That's very important in this case, especially in this case. V du. Yeah. But, well, it is important to set it up correctly, although we're integrating 0, so the answer is going to be 0. So the surface integral of this vector field over that surface is going to be 0, which makes sense. Nothing goes through because the vector field is parallel to the surface at all times. Consequently, nothing is going to get through, as opposed to the lid on top, which is going to give us the area times 2. All right. Oh, so the surface integral of 0, 0, 2 for the entire surface, which is the lid and the side, without the bottom, without bottom lid, over the whole S. Now, S means this and that, is going to be the 2 pi that we found in the previous page. 2 pi was the flux across this surface, the top, equals 2 pi plus 0 that is on the side. So that is 2 pi, which is the same answer we obtained when we used Stokes theorem. So we did this in 2 ways. We can find that directly, surface area, rather surface integral, and then add them together. Or you can use Stokes theorem, and you don't have to add anything together. You can just look at the boundary, this would be the boundary of the surface, and then you're all set. Yep. There are two things that we want to expand on or explore, yeah, which are, in my opinion, very important. And it could be also important to you. It depends how you look at it. Okay, so let's do two explorations. Well, explorations, or expanding this a little bit. So say you have the top, the sides, but then there is part of the floor. The floor is partially closed in. So pretend there's another circle here on the floor. So there is actually all of S, now this is a big surface, is made up by S1, S2, which is the side, and then we're gonna add not a complete lid on the bottom, but a lid with a hole through it. So this is a washer. Okay, so we have S1, S2, and then S3, comma, lid with a hole through it. And let's assume that the radius of the hole is A. Assume radius of hole is A. So A is a constant, and we're going to assume that A is between 0 and 1. Of course, the radius of the entire cylinder is 1, so the radius of the hole has to be smaller than 1, otherwise it wouldn't be a hole. So what would be so S is made up by S1, S2, S3, so that's the top, the side, and then the bottom. But the bottom has a hole in it. So the question is, what is the double integral of 0, 0, 2 with respect to the surface over that big surface, this S? Oftentimes I use this script S instead of that because I don't want to confuse them with fives. So the entire surface, how do we go about that? Well, if we use Stokes Theorem, and we are allowed to use Stokes Theorem because that came from a curl, and we know the curl of what, then we can go ahead and do that. The curl. So this would be the line integral, yep, of 002 dr, but C is going to be that, the hole, the boundary of the hole, which is also the boundary of the surface. Yeah, so that would be C. C is that. It's closing in the bottom. So we have a surface that is not quite close because it has a hole on the bottom. In order to figure this out, let's work on dr here, down here. So R would have to be a cosine of t, a sine of t, and 0. The R is the one that describes the C. R describe C. Okay, and dr would be, oh, I made a mistake there. It cannot be 0, 0, 2. In order to use Stokes theorem, because we're applying Stokes theorem, we cannot have the same vector field, of course. That's a novice mistake, of course. What do we have to have? Well, we have to have the anti-curl or an anti-curl. I'm sure there's many anti-curls. So one anti-curl is negative y, comma, x, comma, 0. The same one we used earlier. Yeah, now we're good. Boy, that was a bad thing to do. dr would have to be negative a sine of t, a cosine of t, and 0. And so that's about it. So this integral becomes negative y. Again, this is x, this is y, this is z. So negative a sine of t, a sine t, comma, x. X is a cosine of t, comma, 0 dotted with negative a sine t, a cosine t, and 0 again, dt, as we go from 0 to 2 pi. And that's, of course, going to give us, I miscalculated, I needed more space, 0 to 2 pi of, well, that's going to be a sine squared t plus a, actually a squared, cosine squared t dt. And then if we factor out a squared, we're going to end up with sine squared plus cosine squared. And that's going to give us 1 times a squared. I hate it to end up there because now this is on the way. So I'm going to continue on the next page. Next page. So we have the double integral of the surface. Which surface? Let's recall what surface we're dealing with. This is an inclined cylinder. That looks too flat. Let me scratch that. Inclined cylinder. Although it doesn't matter because we're not even taking that into account. And then the bottom is a lid with a hole in it of radius a. So 0, 0, 2 with respect to the surface. And then we continue here. That is equal to the integral from 0 to 2 of a squared dt. A squared, 2 pi rather, dt. So a squared is a constant. Factor out the constant, you end up with 2 pi. So we have 2 pi a squared. That is interesting. That is an almost anti-intuitive. Now, what happens? This is an exploration, mind. We're not doing a problem. This is an exploration. We finished a problem. So what happens if we send a to be 0? If a goes to 0, all right, then, so if this shrinks and gets smaller and smaller and smaller, then the double integral s of 0, 0, 2 ds goes to, okay, so if a goes to 0, we're going to go to 2 pi 0 squared. 2 pi times 0 squared, which is the same thing as 0. So if we take the limit as a goes to 0, the surface integral of the whole thing, mind, S1, S2, and the bottom, S3, is going to end up being 0. Now, how can we explain that? Because this is a weird in a way, because if we did the surface integral, okay, so the question is why? Why do we get 0? Okay. Why do we get 0? And you may say, well, we just get 0. But think about this. If you just have the bottom, just the unit circle, nothing else, and we do a surface integral of 0, 0, 2, if we do 0, 2 over that surface with respect to S. We've done this many times, or you should be able to figure this out. It doesn't take too long to figure out that we end up with 2 pi. But we got 2 pi for the other two surfaces, S1 and S2, in our problem. So the question is, shouldn't we get 4 pi instead? How come we're getting 0? That's, I guess, where the question is. Why are we getting 0 and not 4 pi? Somebody may say, wait a minute, we go through the membrane once, and then we go through the other membrane twice, so aren't we getting double? And the reason is no, because of the orientation of the surface. See, the entire surface is well oriented, and that is very, very, very cool, in my opinion. So the orientation is outward. That's the orientation. That's not the vector field. It's always outward. That's the orientation. But the orientation should be should make sense. Should be, it is not continuous on the edge, but it is still outward relative to the solid. So this is the solid. Okay, so the orientation is always outward. So in this case, it would be diagonal. The orientation is the same outward. So on the bottom, the orientation is down. And then on the sides, well, it's sideways. But it's interesting that the orientation on the bottom of a surface that starts out being oriented this outward is going down, which makes sense. So that means that in the unit circle, when we are thinking of the unit circle as part of the bigger surface going on here, we're thinking of this as a negative, having a negative. So the orientation is going the other way. That's what I'm trying to say. So the surface integral, as seen of part of this surface, should be negative 2 pi, not positive 2 pi. And that explains how we obtain 0. So Stokes' theorem takes into account the orientation, and that is very, very, very important to take into account. Yeah. The other thing I wanted to explore, so that is exploration 1, if you will. Explorations, well, let's call it 1. Now, exploration 2. So when we applied the Stokes theorem to example 1 initially, back here, when we initially found the answer to be 2 pi, and this was very, very short, very simple. It took almost more work to figure this out. What else was I going to say? When we did that, we used Stokes' theorem. Oh, we did not take into account the equation. The equation of the top lid was irrelevant. So let's add a note to example 1. So note that when applying Stokes, we did not use the top, or sides for that matter. All we needed was this boundary. That's all we needed. So as a consequence, it doesn't matter as long as you have the same OO2, which is a curl. It doesn't matter what you have here. You can have, you know, some kind of glove. It doesn't matter as long as you have the unit circle the same way as before. You're gonna get 2 pi. It doesn't matter what the surface is up here. So S, as long as this is the unit circle, and we have the same vector field, the double integral of 0, 0, 2 with respect to this surface over that surface S is going to be 2 pi. Yep. Yep. So because we did not take that into account, that's the beauty of Stokes theorem. It doesn't matter what you have. You can have anything you want. Yep. Yep. So that was the second exploration. I thought I was going to tell you one other thing that it just occurred to me, but it escaped my mind. Oh, yeah, I remember. An exploration 3. Okay, so the curl of negative y x o gives us OO2. Is there any other function that could give us the same one? And I'm thinking yes. And it just occurred to me to tell you. So I did not practice this ahead of time. I'm thinking if we put one of them as 2, so let me see if this works. I'm not sure because I just thought of this. So 0, 0. I'm doing the cross product of the gradient in my head. So again, 0, 0 because that would be z, and then 0, 0, and then 2. Yeah. So you don't have to use this vector field. If you use this one in its place, everything we did will work out. So the anti-curl, if you will, we can have different anti-curls. It doesn't have to be this one, it can be this one. Can you come up with a third one? Curl of blank, 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 that gives us 0, 0, 2. And that's something you should find out. All right, we're going to stop this video here. Only one example, but we had a few explorations. And the best way to learn this is to do many problems. All right, we're going to stop here.